Welcome to CW 1.6. Today we're going to be talking about polynomial functions. So if we look at this first question, it says identifying polynomial functions. Determine which of the following are polynomial functions. For those that are, state the degree. So for now, we won't worry about degree. Let's just focus on this polynomial function. So I have a simplified definition for you. So a polynomial function is going to be a function that, one, has real coefficients. So this should be pretty standard. This is just referring to when you guys studied Algebra 2a, you had I sometimes with the root of -1. You won't see that here, so this is more just to be mathematical, or to be mathematically sound. We got our state as real coefficients. But if you do see I anywhere, that's already not a polynomial function. Number two, the exponents are whole numbers. Now that's going to be very important. Okay, the exponents are whole numbers. So whole numbers meaning 0, 1, 2, 3, dot, dot, dot. And the third one is going to be no variables in your denominator. So these are just 3 rules I like to think of when you're trying to figure out is something a polynomial function. So let's go through this quick. Letter A. This one clearly is, so I'll put a happy face. We're not breaking any of these rules here. Number 1 is good, 2 is good, 3 is good. Letter B, this is interesting. Root x. What you do is you rewrite it as x to the 1/2. So recall from Algebra 2a that a root can be rewritten as a fractional exponent. And now we break rule number 2. The exponent is not a whole number. So I'll put a sad face. This is not a polynomial function. For this one, look, you have a denominator with a variable that breaks our rule number 3. That's also a sad face. D is kind of weird. That is just a number. So just a number, if you look at our rules, there are really no rules broken. So yes, this is a polynomial function. By the same logic, E is also a polynomial function. And F, yep, all the rules are okay. So let's put a happy face. So 5 out of 6 actually were, no, 4 out of 6 were actually polynomial functions. So now let's do the degree. So the degree is going to be the largest exponent on a variable when simplified. So simplify is going to be really important. So all of you should highlight this word right there, simplified. So for some of these, it's really easy. If you look at A, there is only one variable there. That's a 4. So the degree is 4. B and C don't apply. If you go to D, 0 is kind of weird. 0 is kind of a special case. For this, we would say no degree. Just so you know, this is kind of weird, so I wouldn't really test you on this fact. This is just for your knowledge. 8 is something I will test you on. So this is considered a non-zero constant. So pretty much anything other than 0. For this, we say the degree is actually 0. And that's because you can think of 8 as 8x to the 0. So that's where that's coming from. But again, to avoid confusion with D, I won't test you on this one because this is kind of a unique situation. So don't worry about this. Just know that constants are going to have a degree of 0. Now F is the weird one. A lot of people want to put 3. However, this is incorrect because of this fact right here. It must be simplified. So I multiply this out to get negative 2x cubed. And you could multiply this thing right here, 2x plus 1. But notice how it's just the largest exponent. So you don't actually want to multiply everything, right? That actually would be kind of a waste of your time. We're just going to focus on this part because this is what's going to create our largest exponent. And the degree on this part is going to be 5 because x to the third times x squared is going to be x to the 5th. We're going to add one more thing to make this problem a little bit more complex. we're going to add in leading term. So I'm going to get rid of this right here. And again, we're going to add in leading term. We're going to use this a lot in class, and I'll refer to it as LT. Put simply, the leading term, it's the term at the front of the function when it's simplified, so simplified is important, and it's written in order. So for A, what we want to do here is I want to write this in order. So I'll just reorder it here. F of x equals negative 3x to the fourth plus 2. And right there, there's our leading term. Negative 3x to the fourth. No problem. For D, we'll skip that because that's kind of a weird one. For E, well, E there's only one term. So I'll just write leading term. That's going to be 8. And F is the cool one. So remember how we multiplied it out? I kind of erased it, but I'll put it back over here. When simplified, so imagine we were actually to multiply this whole thing out. We only care about what's in front. So imagine you have this thing right here, negative 2x to the third. If you multiply this thing out, the biggest power of x that will come out is x squared. So all we care about is this thing right here. So multiply that together, and you're going to get negative 2x to the fifth. That's your leading term. Now, if that didn't make sense, you can actually just do it if you're never sure, or if you're not sure. Multiply it out, x squared minus 2x plus 1, and then distribute. Negative 2x to the fifth plus 4x to the fourth minus 2x to the third. And you can see your leading term is right there. And that's it. Next thing. For the polynomial below, it says find the zeros. So two things here. We're going to highlight zeros and multiplicity. The zeros are really easy. You just write z. And the zeros are essentially your x-intercepts. It's whatever makes the function 0. So in your head, just solve this thing. What makes that 0? That's clearly 2. What makes this one 0? Negative 3. What makes this one 0? 1/2. Now multiplicity is going to be the weird one, or the new one, I should say. Multiplicity, the best way to think of it is going to be the exponent attached to each respective 0. And I'm going to put 0 in quotes because when I say 0 in quotes, I'm referring to each of these expressions that created each individual 0. So for example, this 1/2 came from this expression. The exponent that's attached to it is a 4. So we're going to say the multiplicity is 4. And I just write it directly underneath like that. This negative 3 came from this. So the multiplicity is 2. Let's write 2 right there. And x minus 2, there's no number there, so we assume that's a 1. So there is our multiplicity, 1, 2, and 4. You don't have to put these arrows there. I just put it there to make it more clear. I typically just write the z and the m underneath, and I'll assume they're going to match like that. Okay, so now we're going to go backwards. It says find a polynomial function of degree 3 where the zeros are this. So I really want you guys to know is this word function is very important. As soon as you see like write a function, your instinct has to be to write f of x equals. You need to have this because without this, you're not going to have a function. So again, never forget to just write this out even before you start working. Okay, now we're going to go backwards and think, well, how do you create a function with these zeros? Well, look over here. X minus 2 was 2. X plus 3 was negative 3. X minus half was half. So now we're going to go backwards. So for -3, we're going to write x plus 3. Because if I plug in -3 right here, you get 0. Next one should be x minus 2. And next one should be x minus 5. Now you're probably wondering, how do you know the multiplicities, right? How do we know about these exponents here, here, and here? Well, they're all 1. And we know that because the degree is 3, meaning if I multiply all these things out, I should get x to the 3rd. So let's circle that, and we're done there. Okay, let's go to our next example. So for this one, we're going to be writing down some functions, right? X squared, x to the 4th, x to the 6th, x to the 8th, and so on. We all should know x squared looks like a parabola. What's interesting is, as you keep going up 4, 6, 8, the parabola is just going to get more and more narrow. And that happens forever. And for y cubed, we should all know that's kind of like an S shape like that. If we continue this, 5, 7, 9, 11, the same logic kind of applies. It's just the same shape, it just gets slightly more narrow every time. So you're probably wondering, well, why is that valuable? Well, because knowing that fact, you can actually graph a lot more things now. Like let's say you want to graph this. We're just going to do it generically or very simplified. I can think of this as negative x to the 5th plus 1. So I know x to the 5th, the parent graph should look something like this, because it looks like x cubed. And I'm going to reflect it over the y-axis and shift it up 1. So I just reflect it. And then this thing is going to get shifted up 1. So let's move it up 1 unit. There we go. So for this next one, we see 1/2 x minus 1 to the 4th. So we talked at the very first day, this 1/2 is going to simply stretch the y's by a half. And that minus 1 is going to shift it right 1. And again, we're drawing this generically, so it's not going to be perfect. We know x to the 4th is just going to be a parabola like that. That's our parent. And we're going to shift it 1 to the right, and it's going to be 1/2, or stretched by a factor of 1/2. So we'll just go 1 there. And just do something like that. And that's it.